today is the last lecture of Sabin about Abelian Hall categories, and so you can start when you're ready.
Right. Let's see how this is gonna go. So I'll try to say a few words about r-matrices, and then maybe do some examples based on the feedback I get from the audience and the interests that I've expressed. So the roughly speaking, what's this theory of or renormalized R matrices? So this is a concept. Yeah, that's feasible, no? Yeah. This is a concept sort of brought to the forefront by Kashiwara, Kang, and Kim, and O, in the context of quiver Hecke algebras and quantum groups. And I'm just going to summarize it very briefly. So the main gist of it, because that's not really what my talk is about, but I can probably clarify a lot in a couple of minutes. So let's suppose you have an abelian graded category, very generally speaking. You can imagine it's finite length. I don't know if this theory requires this, but anyway, let's say finite length for this argument, because in all cases it is. So why not? Then a system of renormalized R matrices consists basically of what it sounds like a map. I'm going to write R for any two objects. For any two objects, let's say M and N, and you have a map between it's called R and N, between the composition one way, I should say abelian monoidal category, of course. Very important detail that I forgot to mention. And you have the composition in both ways, and it's such a map. And there's usually some combinatorial data which gives you a shift here. So I'll denote it NN, where so M and N are two general objects, and this lambda is an integer. So this is sort of some combinatorial data that comes along. And this, of course, is the grading shift for this category because it's graded. And I'm writing it like this because in our case, it's the grading shift that's relevant corresponds to this shift here that I was using earlier as well. Okay, so it's that's the data. It's such a map, such a let's say non-zero map. For any two non-zero MN, such that it satisfies set of properties, which I'm not going to write all of them. I think it was not formalized at the very beginning either, but it satisfies such sort of properties. I'm going to write, there are not so many, and they're pretty, some of them are very simple. I'm going to maybe highlight like two of them. So let's say some things, including, let's say, just to get a feeling of what it is. So maybe this one's interesting. The third one on my list would be if you look at the composition of two such morphisms. If you apply this morphism twice, so you do RMN composes with RNM, right? Then this will be non-zero if and only if the pairing MN plus NM is 0. So little things like that. In particular, this one, the point here is that most of these maps, you should think of them as not being isomorphisms. It's very rare that it's an isomorphism. This map between compositions. And maybe so there's some other even more boring ones. Maybe the most elaborate and not necessarily the most interesting, but certainly the most elaborate and probably the most useful is the following one, just to get an idea. Suppose you have three objects, let's call it M and N1 and N2. So you have M, N1, and N2, and you have a map F between N1 and N2, then you can consider the following diagram. So you can either first apply the R map here. I'm gonna start writing the MNs, and or you can first apply, or you can apply identity with F here, and then apply the R map. So you have a square like this. It doesn't necessarily commute. That's part of the point. I'm omitting the shifts because it'd be confusing to include all the shifts. But the point is that we have three cases. Either the pairing Mn1 is equal to either the pairing Mn1 is equal to Mn2. So like this. In which case the diagram commutes. Or one is obviously can be less than the other. In which case the bottom, this composition here, bottom left is 0. Then this composition bottom left composition is 0. And similarly, if the thing is in the opposite, or if the inequality is the opposite, then the top right is 0. This is not very important from the point of view of the general picture. It's just to give you an idea, so that's why I'm squeezing it down there. But this is like there's maybe 2 or 3 more much simpler, not much simpler conditions, and which these maps should satisfy. This is being the most elaborate one, and one of the beautiful things that they show in this theory in a series of papers is, for example, that a category, an Abelian category of finite length with such renormalized r-matrices satisfies many nice properties. For example, if you take consequences, there's many consequences of having such a structure, but in particular, if M and N are simple, let's say if both M and N and the composition of M with itself are simple, sorry, 1 second.
Oh, sorry.
I think she's in the other room or outside.
Okay. Okay. I'll figure it out.
Sorry about that, someone knocked. So if M and N and M composed of M are simple, then the head of the composition M with N is simple. So things like that. All right, so there's
What is head? I mean, I do not understand anything.
I'm sorry?
I do not understand anything of what you said, including the
Okay,
word
great. Let's
head.
clarify it. So as a consequence of having this extra structure of renormalized R matrices, the claim is that if you have two objects, M and N, such that they're simple, and moreover, one of them is what's called real, namely real simple, namely not only is it simple, but it's the composition with itself is still simple. And as a consequence of that, if you take the composition of the product of M and N, you can look at the head of that, meaning
What is head?
meaning the direct sum of all the simple quotients. So it's the largest semi-simple quotient of this guy.
The direct sum of all semi-simple quotients.
So
Yeah,
it's the quotient out of the radical, that's the head.
Oh,
That is the quotient of the radical of the.
okay.
So the category is in general not semi-simple. So you can look at, for example, the different simple quotients it might have, right? And the claim is that in this case, M composed with N only has one simple quotient, the unique one.
Yeah, that's okay. Can I see the blackboard, the whiteboard again, Zongzhu? I prefer to see the whiteboard, not your picture.
Didn't see
Yeah,
that.
good. Yeah, that's good, but I do not understand, especially since they took the name R-matrix. It looks as a graded version of the of commutativity morphism and some possibly braided category, which is not. And so then, what's the origin? I mean, you said mention quantum groups, and so
Right.
what that mean? If, for example, lambda mn is equal to 0 for all m and n.
Then the category would be semi-simple.
Yeah, that's okay. I'm fine with it.
So,
But then
the case is studied is the case when the category is the category of modules over some sort of quiver Hecke algebra. So, for example, in this case, if you look at this category of modules, if you look at quiver Hecke algebras that you can form, you can look at their modules. They have a natural convolution product. It's in some sense completely parallel to what happens with whole products. And so this category of modules of quiver-Hecke algebras is a monoidal category. And people have noticed, I guess, historically, I'm not the biggest expert, but if you study the category of finite dimensional modules, then you have all kinds of phenomena. Like if you look at two simples of this form, then the head is simple, for instance. And so they did many things, but they showed that many of these consequences, as well as others, are follow from. They show that many of these properties follow as a consequence of the existence of R matrices. So how do they describe the R matrices? Well, we can. I don't want to go into that, but it's actually parallel to what the way I'm going to describe it.
Yeah, but I have in mind a different class of examples, which are certainly not Hecke algebras, but in a sense they enjoy similar property. For example, if you have finite dimensional representations of say quantum affine quantized enveloping algebra, yeah, for affine Lie algebra.
That's right.
Yeah, it's not semi-simple.
That's right.
Yeah, and you have this shift lambda, it's some exponent in the power of q. So you have some sort of replacement for the braiding, which is kind of not very difficult to understand. So it's natural properties. And
Yeah,
now, as you formulated, it looks scary. So I'm just curious what kind of examples people have in mind.
Right. So the main examples, I could probably list them, the main ones that I'm familiar with. There's this one. There's one which they also study part of this part of their large study of this theory and associated phenomenon with, as you mentioned, modules over the examples, modules over quantum affine Hecke algebras, so loop algebras. UQLG. So in that case, again, well, yeah, I'm not going to go into the definition, but they show that in both cases, one can, if you look at the wide subcategory of objects in here, then there exists again renormalized r-matrices, and
why do they call them renormalizable, by the way? What's
right. So I think it will become clearer if I show you how it works in the geometric setup, because basically in all cases, while they're fairly different, the philosophically where these maps are come from are the same. So let me illustrate roughly how it works in this geometric setting and it's in a parallel way in a very similar.
Yeah, you see the reason why, I mean, for me, these two examples are indeed very different, because for UQ of G, you have just, sort of a Hopf algebra structure on your quantum group, you can tensor it, and this shift, it appears because your R matrix actually not small r but capital R, something which people knew for a long time in quantum groups. It just depends on the parameters you evaluate. You can consider evaluation representation at one point of a complex line in another one, and when you try to interchange, then you see some meromorphic braiding, and
that's roughly where it comes from. That's right.
yeah, that's true, but it's not that scary as you presented it, because it's the same axioms as as in braided monoidal categories, but just some parameters should be added.
I think it looks a little bit scarier because I'm how can I say I'm looking at the restriction of these bigger there are these I'm looking at the restriction of these sort of maybe the R matrices you have in mind to specific evaluations of them, and that's why the resulting map looks a little bit scarier. But the source of all in these cases are kind of all similar, all the same, and they're kind of what you're talking about. The point of running them like this is because principle, these are the formal properties that you actually need to conclude things like this and so on and so forth. So you can just restate them formally in this way. And in principle, there could be other sources of such data satisfying these properties. But of course, in practice, I don't know of any others.
Okay. So if you mean indeed, when I kind of invented this meromorphic tensor categories long ago in 90s, I did not mean to describe simples. I mean, it's a different problem.
That's right.
Okay, yeah, but if your target is to describe simples, yeah, probably you need.
That's right. And
Yeah,
it's
okay,
a
yeah.
level of, like, for example, quiver Hecke algebras. I think originally people, originally sound like that old, but people studied a lot about these are related to quantum groups by studying projectives.
Yeah.
And at the same time, you can also study simples. And the corresponding canonical basis you get one corresponds to the canonical basis, the other one, the simplest corresponds to dual canonical basis. Originally, it was the former which was studied more originally. The first few.
I understand. So okay. Having in mind indeed application to the whatever dual canonical basis. Yeah.
Yeah.
Okay, good. Thank you.
So this is the dual canonical situations. These are finite modules, finite dimensional modules over this rather than projective modules. Okay? And
Okay.
the analogous thing here for us is that we're restricting to the nilpotent. Remember we had this nilpotent condition where we could have worked on the whole space, but we didn't. We worked on just sheaf supported in the nilpotent. That's sort of analogous to going from just studying arbitrary modules to studying finite dimensional ones. It's not a perfect it's an analogy. It's not a perfect parallel, but it's certainly very similar. Okay?
Yeah, okay.
Right. Yeah, so anyway, so from this point of view, it implies that whatever all these abstract results tell you about objects, about simples or whatever other objects, they will apply in particular in the case of our whole category. Particularly if you take two simples with this property, then the head will also be simple and so on. And this is actually, yeah, I mean, this might seem like an esoteric fact, but it's actually quite, it has some interesting meaning, and I don't know, I'm not sure call it applications, but it's not just a random observation, if you like. Okay, so the point is that this category, this whole Abelian Hall category, so this is the discussion. Fact HQ carries renormalized r-matrices, and these the source for of these guys is a certain deformation of the moduli spaces chi xi xa. So that's what I like to describe a little bit about these deformations, and then how do they help? And as I said, morally, this is very similar to how they're constructed. It's not exactly the same, but morally, it's very similar how all these examples are constructed. In some sense, considering a deformation, and then constructing some sort of our matrix on this deformation, and then restricting to where you're interested. Okay. So for let's see, some deformation. So the idea is the following. So we remember everything happens over nilpotent cones. So we're going to start with some very simple deformations, in fact trivial ones. So I'm going to note this is the nilpotent cone, the product of nilpotent cones associated to our quiver. I'm going to denote by NA. So this is all endomorphisms with eigenvalues 0, with all eigenvalues 0. This is going to be all endomorphisms with eigenvalues z. This is and those have only eigenvalue z, which is a complex number. All right. Notice this is a trivial deformation in the sense that I could just take a nilpotent and add z times the identity, and that identifies this into a trivial family over z over a1. Sorry. Okay, so it's a trivial family, and you similarly have analogous spaces for spaces for the other moduli spaces that showed up. So you have MA, which doesn't change because it contains everything. But inside of here, you have MAZ, which is, again, literally repeat the whole definition of MA from earlier, but insisting that the eigenvalues which show up are all Z. And you also have MASAZ, so on. Okay. And now that's the first thing we need to consider, these trivial deformations. And now we need to consider some sort of convolution product for such slightly larger. So of course in here you have MA, SA, because you can restrict to Z equals 0. So we this is our moduli spaces mod out by GA. And we want to consider a convolution product with such objects. So you should think of Z as a spectral parameter, if that makes any sense for sort of, I'm trying to connect it to what you were asking earlier. This is going to play the role of the spectral parameter. And there's sort of spectral parameters in all these stories. So one can do the same construction as before. So I'm going to sort of try and draw it here. You're going to have MA, map space. Let's draw the big space then. So for the convolution product, you're going to have, we have MAB, SAB, if you remember, this sort of intermediate space, which map to MA, SA cross MB, And now we're going to do a sort of a deformed version to it. So we're going to deform this one with some parameters Z1, this one with some parameters Z2. So we have two parameters. And this space is going to be denoted Z1, Z2. And it's going to consist of, so I'm going to write it. So it's the same condition as before. So again, it's pairs phi x, the same types of endomorphisms plus the maps between the vector spaces vi. Except now, remember here we're looking at an endomorphism of VA plus B, which fixed VA inside of VA plus B. So we have the same standard condition, but we want that. Let me say it like this: we want that phi. Well, the obvious thing, so it maps to that. So phi restricted to VAs has eigenvalues Z1, and phi restricted to VB, I think I called it prime last time, eigenvalues Z2. So it's a sort of an obvious deformation of this guy. Okay, and there's an obvious map here. The slightly less obvious map is the multiplication map, MAB, because it maps to another space, which I'll denote, which is a little bit different, but not so much. I'll denote it by this small subtlety. I'll denote it this way, MAB. And what this space is, right here, I need more space. What the space is, let me explain like this at least. So MS A plus B, parentheses AB, Z1, Z2. This will map over the analogous space where as if, so this makes sense for any quiver. Of course, you can take quiver without any edges, and that's what the nilpotent stuff is. So there's an analogous space for this, and I'll describe this guy first, and then this one will just be built on top. It's really about this datum, about the endomorphisms datum. So this would be A plus B. I guess there's no S here, so it's just one AB, Z1, Z2. So they're going to be again intersection of vector bundles, two vector bundles inside of a third vector bundle, just like before. And what is this guy? So this guy is, you can look at endomorphisms. It's going to be you can look at endomorphism phi with say with Z. If you look at the Z, remember this depends on two parameters. If you look at the Z1 eigenspace of dimension A and Z2 eigenspace. So imagine Z1 and Z2 are different, so you can talk about their eigenspaces. With the easiest way of describing it. And you can take the closure of this locus. So it's sort of you sort of want to know where this has nothing to do with the extra arrows, with the extra bundle stuff. You can just put this at the level of nilpotent cones. You can look at the nilpotent cone NAZ, NAZ1, NAZ2, and look at the corresponding space here and see sort of where it maps naturally, and it maps naturally to a space like this. Okay. And then this guy just built above it just like normally, just instead of having a base given by nilpotent things, you have a space given by such these. And of course, the usual and the groups don't change, like the same groups act. So you can still have GA add here, GB acting here, I guess I call it PAB acting here, and so on. Nothing has changed. And then you define the convolution product for objects on these deformed spaces, just like before. So, so what we're going to do is the following. We want to we're going to try and use these deformations to get us the renormalized r-matrices as follows. So let's take two objects, FA inside of two of our original moduli spaces. Okay, this is XA and XB. I just wrote it like that because I want to emphasize something. So given such an object, you can always cook up a trivial deformation of this object to an object on here. This was a trivial deformation, and this was a trivial deformation over it, just because the construction over it is the same. So once the base is trivial, so are the fibers. So you can take your sheaf and just trivially deform it. I'm going to denote it by a tilde. So this is in co of M A S A Z1, just to keep track of the parameters. Whatever GA. And likewise, you get an element at beta and the same thing, the V. Okay, so notation looks a little bit ugly, but really all you're doing is you're taking your object you're interested in and you're deforming it trivially over these guys. And then you can define the product of these guys. Of course, you can define the following product for any two objects in here and here, but I'm particularly interested in objects of this form, which come from a deformation of this guy. And you define it the obvious way. You pull back, just like before. And with the same shifts as you had before, which I'm not going to write again. Exactly the same expression. Okay. So what's the key fact about these? So these now live on. So this guy, it lives on. Is a coherent object on one of these guys. A B S A plus B Z1 Z2. Okay, and in particular, these spaces are naturally mapped to A2. We have the two spectral parameters in A2. Okay, so now we have given two objects. We have two objects. We have this object, and of course we can also take it in the opposite direction of the product. We have in particular this object on this larger space. It's naturally lives over A2. All right. And so what are the main two properties of these objects? I'll summarize them. Let's see what time it is. So the two main properties is that one, we're interested in what happens to this family over the diagonal inside of A2 and away from the diagonal inside of A2. So over the diagonal inside of A2, so this is where
It's better not to write there because it's
I remember now. Thank you. Over the diagonal inside of A2, this is the locus where Z1 is equal to Z2. This family is trivial. So MAB SA plus B Z1 Z2 restricted to diagonal is trivial. Okay. So in other words, it's isomorphic to just the moduli space we were interested in originally. And A plus B Z1. Oh, sorry. The moduli space is across delta A1. Okay. So they're trivial over the diagonal. And away from the diagonal, it's a little more complicated. So in particular, let me write it like this. In particular, if you look at the product and you're restricted to say a point on the diagonal ZZ, then you just get the original product. The space is the original space, and the restriction of this thing is, I mean, it's not in particular, but doesn't follow formally, but when you restrict it over the diagonal, you're just recovering the original picture, which is not surprising because over the diagonal, both eigenvalues are the same, particularly if they're both zero, then you can see that all the eigenvalues are zero, so you're just dealing with nilpotent matrices. So you recover the original story. Away from the diagonal, so let's say over A2 minus the diagonal. One has the following diagram. Now I'm trying to decide, given how long this is taking, I'll have to write the diagram or just jump to the. I'll write the diagram because it summarizes a lot, and then we can just jump. Obviously, I'm not going to prove it because it's a lot of just a bunch of diagram chases and a little bit of linear algebra. But one has the following diagram. So over this, one has a commutative diagram, which looks like the following. So let's see, how can we go? One has A2 minus delta. You see that? Yeah, that's good. One has A2 minus delta. Let me just write it down. Now I'll explain it. Mhm. Almost there. You see that part? Yeah, it's okay. And here has let's call this one. So it's the same thing backwards. All right, I'm trying to squeeze it in there. Ooh, okay. So let's parse what I just wrote. So let's see what we got here. This S is just switching the exchanging the factors. Let me make sure I didn't write something wrong, because it's easy to switch some of these by mistake. So S, both of these S's exchanges factors. Mainly, this is just exchanging Z1, Z2, and this was just exchanging them. And the claim is that that extends to the rest of the diagram, which is the harder part, to involutions tau and tau hat. And I could at least explain tau, but that would take a little bit of time, and then tau hat again takes a little bit more time. So I'm just going to leave it at that. The claim is that such a diagram exists, and so let me skip over that. And so what's the moral of this? What's the point of this? Let me try to explain. Let me jump to the conclusion. So now let's look at FB tilde FA tilde. This is all sort of scooped from there's some paper that I have. So even though I'm skipping a lot of things, you can just look it up, the details. The point is that we can look at the product in the opposite order, FB-FA instead of FA-FB. And now so that's an object that lives here. And now let's apply tau, or I guess here, now let's apply tau, so let's apply tau upper star. And now let's restrict the diagonal. This is all happening away from the diagonal. So J is the restriction to away from diagonal. So everything that lies away from the diagonal. So in other words, I take this, I apply tau upper star, and then I restrict to the diagonal. And then there is basically a diagram chase, which I haven't written down, but it's just a bunch of commuting squares and stuff. And if you just follow your nose, you get that this is the same thing as J upper star of FA, FB in the opposite order. So what does this mean? This means that if you look at the product this way, then and you apply this map, you apply the pullback of this tau, then away from the diagonal, you recover it switches the two products. Okay, you're gonna have an isomorphism away from the diagonal between the pullback of this one and the product in the opposite order. That's the consequence of that, and this is an easy consequence from that. The harder part is showing that such a diagram exists. This is just diagram chasing. So at the same time, so this is what happens away from the diagonal. Where at the same time on the diagonal, you have, if you look at the product in one order, and you restrict to the diagonal, you get, as we basically what I wrote here. If you look at this product in one order, in the restricted diagonal, you get to a point on the diagonal, you get this. So if you restricted a whole diagonal, you get the trivial deformation of that. And if you do it to this one, if you restrict a diagonal, this guy, you get the same thing, in fact. Okay? Wait, did I copy this wrong? You get, and you check. Yeah, you get the same thing. Okay. So what's really happening here? Well, so what's the moral of this? We're almost there. So let's let me just denote by G the let's take AA FA cross. This is really the moral where I'm trying to get with this. And even if you don't follow it, I think this is the key point now. So let's look at this product in one order, and let's restrict it to the anti-diagonal. Z minus Z. Okay? And likewise for the other one, for the other product. So let's take G prime to be the opposite. And restrict to the anti-diagonal. Then the claim is that if you follow what I wrote and follow through, then you get the following three facts. One is that if you restrict G to 0, so this is over A1 now. So if you restrict G to 0, you get FA cross composed with FB. Likewise, if you restrict G prime to 0, you get FA composed with F. You get FB composed with FA. And 3, away from the diagonal, G prime restricted to the anti-diagonal minus 0 is actually isomorphic. G restricted to diagonal minus 0 is isomorphic to G prime restricted to diagonal minus 0. Away from the diagonal, there's this isomorphism between the two products given basically by this tab, by this fact. Okay? By this tab. So what does that mean? That means that you can look at, almost there, that means that you can look at the space of Helms between these two objects. Let's say you look at M, which is say the degree 0 Helm between these two guys, right? Which is a module over the base. This is a CZ module where the Z here is the coordinate of the anti-diagonal. And so it's and away from the origin, away from Z equals 0, these two things are isomorphic by this isomorphism. So what you can do is you can take that isomorphism and multiply it by some large power of Z, so that it becomes it extends to the whole thing, and you can take the minimal such power. So this map, so let's say M restricted to the diagonal minus 0, right? Is isomorphic to just endomorphisms of G, and so you can take here the identity, and this will uniquely will uniquely extend to a map to some to an element to an actual element of the whole M. So in other words, to some R from G to G prime. How do you just extend? You just multiply it by enough powers of Z so that it extends. But of course, if you multiply by a huge number of Z's, then the restriction when you restrict to Z equals 0 will be 0. So you take the minimum number so that it's not 0. To some, so in other words, to some things like this, such that its restriction is not 0. Okay? Just the minimal multiple you need to take so that such that when it extends and you restrict it, you get something not 0. And then and that's it. And this restriction is going to be your map R between FA and FB is your this big R restricted to 0. Okay. And I'm omitting some shifts here. Of course, you're going to get some equivariant shift here because once you restrict away from 0, away from the diagonal, it's over C star, so you're losing the gradient. So when you extend it here, you're gonna have to pick up some possible shift, and this shift you pick up is this lambda invariant that you see later. So let's say S is equal to lambda FA FB. Whatever shift you pick up, they have much control over that. Okay, so again, to recap, because this is a lot of the spaces here have sort of a factorization-like property. It's not really a factorization space, what we have here.
Why not?
Factorization spaces, in the sense that you have these deformations such that away from the diagonal, the products in one order is isomorphic to the product in the other order, and over the diagonal, well, you just get the usual product you started with in the same order. So you can use that in this way to get a map between. This is just a general procedure to get a map between the two deformed things, and in particular, you can take an appropriate multiple so that the restriction of that map is not 0, and that's this R you get.
Yeah, but why it's not a consequence of the existence of some factorization structure? It reminds very much of what I saw, like in Billings and Drinfeld chiral algebras when they.
That's right. It's exactly the same philosophy, and the philosophy for obtaining it is exactly the same as how we obtained it in a paper with Harold, and when we did when we considered the case of Coulomb categories. But in that case, those things are actually factorization spaces. In this case, they're not literally factorization spaces. How can I say this? Even though there's an isomorph, they're just not. I mean, even though there exists this isomorphism away from 0, they're not literally the product. Like okay. A factorization space says somehow, well, you know what it says, but it says that when you look, what I say, but in particular factorization space, when you look over 0, you just get the original space back, kind of thing, right? Mm-hmm. That's not literally what's happening here, and so yeah, so these are not literally factorization spaces, but they contain enough of the structure that it allows you to take whatever two things you're interested in and take a product in one order and another order and somehow deform it in a natural way so that away from 0, that deformation is the same. But let me think. I mean, even making sense of what does it mean in this for it to be a factorization space in this context is a little bit unclear because for each A you have the space and of course when you take the product of two, that's sort of the convolution diagram for two such things in whichever order, the space grows and gets bigger, right? In the affine Grassmannian, somehow the point is that it grows bigger, but the affine Grassmannian is infinite dimensional, so you're embedding this into a bigger piece, and so you do have this sort of factorization picture.
I don't know if you would try to describe it for fine Grassmannian in terms of orbits, you also will have some dependent, you see something will grow bigger, but I don't know. Yeah, it's very interesting, and I don't know what's what's really going on here. Yeah.
Like if you do, yeah, I forget exactly the details, but if you do like even a dimensional count, it doesn't, it's not literally a factorization space.
Yeah.
Um, I need
Okay.
to
Yeah.
investigate to clarify that.
I should think about it because
It's exactly the same principle as in the case of Coulomb categories or the affine Grassmannian, but the spaces are not exactly the same. And in particular, this deformation that I described is has a difference, has the same key properties for defining these guys, but has a different structure.
and may I
Maybe
ask
like,
you,
for example, I'll say something about example, these Hall categories look very similar in many ways to at least pick parts of the affine. If you look at, if you start with a quiver, right?
yeah.
You pick the corresponding Abelian category here. This is what we're studying here. Or you can look at the corresponding, I mean, so that's this category. On the other hand, you can fix, if you fix two-dimension vectors, that's what's weird. If you fix two-dimension vectors, and then you can look at the corresponding Coulomb category. I guess we used to call it KP Q, but this depends on the dimension vectors. Okay, and this category here looks many ways similar to this one, in the sense that this one is it's bigger at the same time. It's sort of a doubling of this one. This is sort of the whole quantum group versus half of it, just the positive half. At the same time, it's a quotient of this one, indexed by n and n. So making that, while it looks very similar, making that connection directly, geometrically, you can get sort of a way, there's an obvious way you can try to do it, and it looks very promising until it just doesn't work. So I have some ideas about how to relate these two categories, but they're very indirect. Even though geometrically they look like they're very closely related, and algebraically they look, when you look at relations and when you do computations, they look very similar. I cannot get them to work together.
Yeah, it's a bit, you see, I've been thinking actually, yeah, still thinking, maybe you can tell. Your category with Harold, it's sort of a UV description of the category of line operators. And I mean, I spoke to Gayota and also some other people. The question is about the description in the infrared when you have what they call BPS quiver. So you do have a BPS quiver and you want to construct a monoidal category, and the functor from your category to the monoidal category associated with that BPS quiver. And yeah, your HQ, I mean, it's not exactly the same. I mean, David proposed to consider the category of bimodules or this cohomological Hall algebra, which we constructed with Maxim 15 years ago, but it's not literally true. So it has to be modified. And I'm just curious, I don't know. It also has renormalizable matrices. I don't know. Maybe you know he wrote paper, some physics paper about
Yeah, so there is, for example, if anything, I would expect a functor, if there is one, I would expect a functor in this direction because these are sort of in some sense quotients of this guy. But and there is like a paper like a year ago where they consider not that it is category, but the analogous thing. Strangely enough, his functor seems to be, I suppose it's a very physicsy paper, but the functor seems to be going in the opposite direction. Anyway, yeah. So I don't really. My feeling about this is that these two categories look the same, not because there's an actual direct link, but because they're related to a third category here. And so there's a natural map from a third category this way and that way, and they're related as a result of that. And this category here should be something like the modules of a quiver-Hecke algebras. Okay, so we had this recent paper with Eric Massaro where we're defining a functor from here to here. And there should be similarly a functor from here to here, and somehow from some category of quiver-Hecke algebras, and so these two should be related via. I mean, I'm not saying it should be, but that's the only way I can actually see something actually working concretely is to relate them by this third category. In particular, the set of simples here will agree with. It can take in the context of quiver-Hecke algebra. This is something Kashiwara and all these collaborators have studied. You can study certain quotients of the whole category of modules over quiver-Hecke algebras, and depending on which quotient you study, you will get exactly the simples in here corresponding to the simples in there by this functor. And if you don't take any quotient, then you get the whole thing. So you will be able to see what I'm saying here, namely somehow this is somehow a quotient of that guy, in the sense that this is really kind of more or less should be equivalent to quiver-Hecke algebras in some sense. And then if you take some sort of quotient, then you get these things. But I don't know if one will be able to construct a direct functor between them.
Yeah, but for your KP, there is a cluster category structure, yeah. For your for HQ, huh?
Yeah, no, you're right. No, there shouldn't be. Right. So for this one, there's a cluster structure. That's right. You're right.
Yeah, and for HQ, for
Actually,
the
I don't suspect, but I think it's analogous to here, right? If you look at quiver-Hecke algebras,
yeah.
the whole category of all modules, I don't think there's a cluster structure on that. But if you take certain subcategories described by some combinatorial data, then on those subcategories you have cluster structure. The analogous to the picture here. So that cluster structure will correspond to the one here. But if you don't but the whole thing will correspond to HQ. And if you don't take these quotients, this sort of subcategories, then you will not see a cluster structure in general in some limited situations.
Yeah, so neither of these two functors are equivalent.
Rather than these quotients.
Yeah, interesting. Yeah.
And obviously one would expect the r-matrices to kind of all match together.
And the Youngian, I mean, the Youngians, because I mean, Tudor Dimofte, he convinced me somehow that there should be always a graded Youngian somewhere in the description of the correct category, the big or the small one. Do you see it here? For KP, maybe your KP is just represented.
Right. So grade Youngian or
Yeah, or toroidal, whatever.
That's what I want to say. These things look very similar. Here, there's natural generators, and I apologize, I'm not going to get to talk about too many examples. But here there's natural generators, right, given by, when you take the dimension vectors 1, 0, 0, 0, this is just a point. And you can take, it's a C star point on C star, so you can take the natural generators corresponding to the characters. This would be called like EIN, where this is the character and this is the vertex. So you have natural generators here, which generate either in this case the quantum affine algebra, or analogously the level of K over the cohomology, the Yangian. And analogously here, you have some natural generators corresponding to, basically the objects corresponding to fundamentals at each vertex. So each vertex you can take the corresponding fundamental omega 1, and on it put a line bundle indexed by an integer, and those give you generators. And those should, in this case, you should give you a generator of the whole thing. In this case, you should give you a generator of these truncated. You should give you a generator of the whole thing modulo some relations, which gives you these truncated quantum affine algebras or truncated Yangians. It's completely parallel. And then the simplest objects on each side give you naturally these generators.
Yeah, sounds good. Sorry for destroying the last part of your talk. You wanted
I
to.
dragged it too much. I probably shouldn't have.
Yeah. But this, it's very, very, very interesting already. I don't know. Okay, maybe we'll take some questions from the audience. Are there any questions?
Yes, so you need this small r matrix and to show that the whole algebra has some sort of commutativity. So you can then see the cluster algebra structure. Is that the reason of the small r matrix coming to play?
So it's not really, so it's not going to be commutative, only a small parts of it. But right.
Commutative in some sense. See that.
And you have an initial seed, for example, and all those objects in the initial seed should commute. And that will correspond to the fact that if you look at the R maps for the objects in the initial seed, they will commute.
Oh, I see. So that's what but the special properties of the simples.
Yeah. And basically, in general, all you see is that if you take a product Mn in one direction, you get things like, for example, you might get a simple here and another simple there. And when you take the product with some shifts, and when you take the product in the opposite way, you'll see the same kind of simples, but in the opposite order with some other shifts. So at the level of the categories or even growth-ny groups, if you keep track of the shifts, these things don't equal to each other. But at the level of growth-ny groups, if you kill the shifts, in other words, you set the quantum parameter to 1, then they will be. Well, obviously, the class of this is the same as in both cases. It's S plus S prime. So that sort of explains why when Q equals 1, these algebras are actually commutative.
I see.
Right. And by the way, the R matrix here in this particular case would be, it's actually equal to this that's not the definition. It turns out to be equal to this composition from here to here and from here to here. That's an R matrix one way and an R matrix in the other way. So in some sense, it kind of measures a little bit of how things are commutative, but almost always, most objects will not commute.
I see.
Of course, they will commute at the level of growth-ny groups if you set the quantum parameter to 1.
I mean, the cluster structure is also in the non-commutative sense, right? Cluster, it should be the quantum cluster sense.
Yeah, exactly, the quantum cluster. So things will not commute unless, for example, the objects are in the same seed.
Okay. Thank you.
Yeah, by the way, your r-matrices, the definition is complicated. Are they computable in examples?
Yeah, that's interesting. So practically speaking, I could not compute anything directly from the definition. So you compute them indirectly. For example, if you know that m and n are so in other words, one of the extra things you show is that, remember I said that the head of mn under some conditions is simple. Well, in fact, not only the way you show it, in fact, is using the R matrix to show that the image of this map R is a simple. And it's the head, and it's the tail of this guy. So in particular, the way you can show, I can understand what the map is if in that case there's a simple head, there it is, and that simple head is actually the simple tail of this guy, and the R matrix is a composition from here to here, from here to here. So in practice, the way you understand the R matrices is you take your objects, you understand what they look like by whatever other means, just by direct computation, and then you indirectly conclude, and then you can conclude that the R matrix is this composition. But otherwise, there's no way of getting at it. So from a practical point of view, the existence of the R matrix, apart from philosophically being quite interesting, is just tells you that in many cases you know for sure, for example, that the head will be simple. But actually computing what the R matrix is, I've never done it directly from the definition.
It's interesting. In that old story with graded Hecke algebras, did they compute them somehow?
No, I think even, yeah, I don't know some of the detail, but even there it's very hard. Like, I think there's paper just written to figure out, these lambdas in some cases.
Yeah.
Lambdas are the shit.
Yeah, because for the quantum affine for the quantum groups, there is what people call the universal quantum R matrix, R is capital, and so it induces this R matrix, whatever. Commutativity morphism for finite dimensional representations, but it's not geometric, it's some formula.
Yeah.
So yeah, and here it's
Yeah, here it's very geometric. It's sort of the opposite. It's
yeah,
natural,
yeah,
but you cannot compute it directly.
yeah, I see.
Directly figure out what it must have been,
Yeah,
which is
I
somehow
mean,
the usefulness, but
so it's
you
geometric.
mentioned about the quiver-Hecke algebra where the small R matrix was used, and that's quiver-Hecke algebra was coming from this semi-simple graded monodal category, which produced by Lustig in
yeah,
the constructible sense.
yeah.
So are this kind of lambda appearing in Lustig's work?
Yeah, I don't know how to see it from Lucis work from that point of view.
Uh-huh. I mean, in his case, his category consists of all the semi-simple complexes. You always have a
I think
degree
these are
shifting
more
given the
closely
power
related.
of Q.
I think, if I remember correctly, those things are more closely related to sort of projective objects in these categories. So somehow they don't capture as, am I wrong?
Yes, in terms of the representations of those quiver-Hecke algebras and the canonical basis corresponding to the projective
Yeah,
objects,
they correspond
and
to,
simple perverse shifts
yeah,
in Lustig's category.
that's right. So I think you need some sort of geometric analog of the simples, of the finite dimension, at least, to be able to then ask, okay, so what are, geometrically speaking, what are the R matrices?
But that is in the constructible sense.
Yeah, the constructible sense, yeah.
So, and you are doing in the coherent sense. So I was wondering whether or anybody has repeated Lustig's construction completely using the coherent setting.
Well, I mean, in some sense, some of the stuff, that's what it is, right? I mean,
Yeah.
I don't know, to clarify exactly which listic stuff you have in mind precisely, but
Uh-huh. Yeah, he was using all this special gig, and basically he was taking a very small part of the much larger Hall algebra, but taking this every stage taking a stronger resolution type and using the push forward. So I had a feeling that uh, you probably know how to do it.
Yeah, maybe.
Okay, any more questions? If not, then Sabin, thank you very much. So very inspiring and interesting. And
Thank you.
and if there is a paper, if people will have more questions, they can read your paper and email to you, yeah, with the questions.
Yeah, and sorry I didn't get to talking about the the Jordan quiver case, but I have this paper that's in the process of being written. That's exactly about that. So if you're interested, I can.
Yeah, sure. Certainly I do.
Mhm.
Yeah, because I'm interested in this
Okay.
from yeah, I do. I don't know other people, so yeah. Okay. All right. Well, then, thank you very much.
Thanks
And
for your
once
time.
again. And so this is it for today. Thank you. Bye.
Bye.